Welcome to customization points that suck less, or there's a funny story with this title. I presented a version of this talk at C++ Now this year in Aspen, Colorado. And before the conference, there's always a list of prelections that were selected for the conference sent to all the speakers so that everybody can say, oh, I would like to not conflict with that talk or be after them or whatever. And the list of, there was a limit of characters in the name that was displayed on that list. And the limit was exactly that. From this title, the last word has disappeared. Hopefully that's not a sign of something. All right. Oh, this way. All right. Okay, so this talk kind of has two parts. The first one will be useful to everybody who writes C++ right now because it's like the status quo. And the other one is some information about the future, some information about a project that I've been working on and experimenting and so on. All right, so what is a customization point? It's good to know what we are talking about, right? A customization point is anything that allows us to hook into the functionality of some library we are using. So however we can change the behavior in a well-defined manner that the author intended us to, that's going to be a customization point. And I know that some people don't think this is an important problem, but there's been a relatively high volume of questions, like design questions for library design or usage questions flowing on stud proposals, or which is like a public mailing list for everybody who wants to get some initial comments on a proposal he's maybe going to present to the standards committee of C++. Or on the reflectors, which is like the internal version of that, so internal discussion forum. And there's one particular example that will appear a few times that's been added to C++ recently that shows that we don't really know how to make a good customization point in the language. All right. So there is three existing techniques that I want to talk about. The first one of them is template specializations. An example of this is a thing that you've probably encountered at some point, standard hash. If you want to use like an unordered map or an unordered set without explicitly saying this is the way I want to hash my objects, my keys, you're going to have to specialize a template in the namespace std in a way that's going to look something like this. This is a lot of code, right? To just say I want to hash the value inside me. We can shorter this a little bit. So we can just say specialize this thing that's in namespace std, and it's called hash. We can live with this, right? This is like a pattern that we've seen many times. We can repeat it. But we don't have to repeat it very frequently, so no problem. Unless we actually put the structure that we are interested in into a namespace. If I want to achieve the exact same behavior as previously, so as this, with this structure, what's the next character that I have to write? Curly brace. At some point they are missing, yes, but in this case, yes, I have to close the namespace I'm currently in. Because the rules of C++ tell us that we cannot specialize a template that's not somewhere inside our current namespace. And the namespace std is definitely not within, what was that, foo. So we have to exit wherever we are and go specialize there. A naive way to try to say what we meant without actually like escaping all the namespaces would be something like this. This is not currently valid C++, but there is a proposal, number P0665, which I had the pleasure to present for the author in Toronto, that is intending to make this valid code and do what we expect it to do. But it's a long time until we will get this, because there is some concerns about how to actually specify what it does. So the discussion is going to probably be long. So having to escape all the namespaces is tiresome because there's a lot of typing we have to do. We can be deep in some namespaces. C++ 17 helps because we can now enter multiple namespaces at once. We don't have to each time repeat namespace, blah, open brace, namespace, foo, open brace. One minor point that probably doesn't come up frequently is that once we have something like this, so we escape all our namespaces and we specialize something from standard, we can no longer include this particular header inside a namespace. Which, as I said, is not a frequent case, but my personal use case for this is I have a library that's used by its own testing framework. So I want to use a tested version to test the new version. So I want to have two copies, so I just include into a namespace. But this doesn't work when I have to go and specialize something from standard. The particular feature of C++ 17 that I wanted to tell you about with its not very good customization points is structured bindings. There's going to be some code that explains exactly how this works, but among the customization points for structured bindings, there is two struct templates inside namespace std. It's tuple size and tuple element. Another kind of minor point, but both are defined in tuple, and this header is not freestanding. So if you want to use structured bindings inside a program that's intended to run on bare hardware, for example, you might have trouble because this header might not be present, and you might have to implement it yourself and provide all the declarations and so on. And also you have to escape all the namespaces. Again, it's the same problem as with standard hash. And you'll see the extent of the problem slightly later. Oh yeah, and there is more than a single one. So there is at least two, and you are probably going to have to specialize, to have many more specialization than just two. So as I said, there is a paper that helps us with the problem of having to escape all the namespaces. But other problems still exist. The standard uses them in a very weird way sometimes. So instead of just having one structure, we have to specialize and use some interface that makes sense. We have to specialize we have to create many specializations at once for a single feature to work. And also, there is no way to inherit the default behavior somebody intended for our thing. Which is a problem that comes from the fact that this technique isn't really a core language feature per se. That is, class templates are meant as class template specializations are meant as a way to provide a separate definition for some cases, not something that takes parts of the original definition and adds to them or modifies them. So say we have something called container traits, which allows us to say how to interact with an object like it was a container. So this is the basic interface of a container, right? Something of a basic interface. We have some iterators, the begin and end, and we have size, right? Somebody provided us with something that looks a bit like a container, but not exactly. The size is wrong, has the wrong name. So the initial impression might be that we just have to say, okay, for container traits of some quasi-container, we only need to say that the size is actually calling element count. So the initial attempt might look something like this, which is wrong because now we no longer have a definition of begin and end. There is a way to walk around this, but it's not very pretty. We have to create a separate class template that specifies the default behavior, inherit from it in the trait, and then we can inherit from it again. Because if we try to inherit from the base template in the previous case, it would just not work. We would try to inherit from ourselves. And this is a direct consequence of trying to hack around in the language using features for something different than they were meant to be used for. All right. Another technique that's used very extensively is ADL. How many of you know what ADL is? How many of you know how ADL works? All right. That's the proper reaction. Not many people know how ADL works. So ADL means the argument-dependent lookup, which is a thing that's kind of weird because the way we call a function sometimes pulls more overloads to the number of overloads we are considering. So when we are doing an unqualified call, so we don't name a namespace, we just name the function and provide the arguments, then all the arguments, all the overloads of this function from associated namespaces of the arguments of the call are also considered for the call. And this is a problem that this is a language mechanism that was intended to solve the use case of operators. C++ allows overloading of operators. But when we do something like this, when we say A plus B, there is no way we can specify a namespace for the operator, right? And we don't want all the operators to live in the global namespace. That would be bad. So the way this works is the language rewrites the addition on the right of this construction to a function call of operator plus, and then looks up the namespaces of both the arguments, searches for all the operators that are possible there, and chooses the one that fits best. But there is problems with this approach. It's an ad hoc solution to a problem that somebody realized and didn't think of consequences of. So one particular example that comes up very frequently from the standard library is std swap, which just swaps two elements. And it's a ADL customization point, so whenever we call swap, we are supposed to do it in a very particular way. There is a default implementation of this function in the namespace std that just uses move semantics to swap them around using a temporary. And say we are implementing another part of the standard library called iter swap, which just swaps the elements pointed to by the two iterators we pass to it. So to actually call swap in a proper way, the way we are supposed to call it, we have to write something like this. So first we say we are using the overload from the namespace std, because that's where the base case lives. The primary behavior, right? The default behavior. And then we call swap on the two arguments that we mean to swap. And what happens here is, if there is an overload in the associated namespaces of the arguments, that overload is probably going to be selected. Because the one in namespace std is a template, that's probably going to lose the overload resolution. And this causes problems. This is two separate statements that we have to actually call this function properly, to do what is intended of us. So Sphinx is hard. How many of you know what Sphinx is? Okay, that's some hands. Sphinx is basically a way to say, okay, this function is only valid if something. So in this case, what we actually mean to say is this function is only valid if the expression between the parentheses of the decal type is valid. How exactly this works doesn't matter right now. But we are trying to detect whether that expression is a valid call. Anybody sees a problem? Exactly, yes. The swap doesn't see the overload in namespace std because we are not doing a using in there. So swap isn't in scope, the standard swap. So we will sometimes detect that this function call is not correct, even though it is. Because we are not using the default behavior. We are not opting into the default behavior. The way to go around this problem is to write something that's not particularly pretty. So we create a separate namespace. We pull all the names that we are interested in into that namespace. We create an overload inside that namespace that sees all those overloads that we are interested in, and then uses ADL inside, because the call is unqualified. So it will use ADL. And then we just use that function instead of just swap. But this is not pretty. This is very particularly ugly. And repeating this every time we actually want to do this is very bad. So structured bindings again. To actually get the elements that we are assigning names to that, you'll see a code example in a minute, if you don't know what I'm talking about. But to actually get the elements of an object that we are destructuring, we have to call get. By default, it's looked up as a member. If it isn't there, it's looked up using ADL. And ADL only, which means that only ADL is used. No normal overload resolution happens. This is the same when you're using range-based for loop. The begin and end are going to be looked up only using ADL, nothing else. Which is like the only three functions in the language that can be called this way. We cannot use this like directly anywhere. Okay, so the idea of structured bindings is something like this. We have a class that has two members, and we want to allow to bind specific names to references to those members. So in the last line, member and another aren't variables. They are just references to an underlying object. So what is actually initialized there is an object of type A, and those are just names into that object. And the way to tell, the language knows what to do when we are doing this with arrays. It knows what to do when we are doing this with just structs, aggregates, that only have members, no access specifiers or whatever. But it doesn't know how to do this in the general case. We have to tell it. And it looks something like this. I think this compiles. I've tried a slightly simpler version and it compiled. I think this is correct. So first we have to tell it how many elements there are in the object. Then we have to specify the type of the first one, the type of the second one. And then we have to provide a get that will actually extract those members. This is ugly, right? Structured bindings are C++ 17, and C++ 17 gives us a feature that makes this slightly less bad, only slightly. So again, the same thing. And in the get function, we can use something that's called if consexpr. It's an if that's resolved at compile time. So only the matching return will be used. So this is slightly less horrible because we don't have to like specialize a function template which follows some very weird rules. And we can just write a single function, but this is not a good customization point. There was a lot of discussion on the committee about this, about how to approach this. And why it looks this way is followed from, well, we can fix this later. We just want to ship the feature. It works for a lot of type that users will want to use with this. So it's shipped. I don't think this is going away anytime ever. So this is my primary example of how to go wrong at designing a customization point. It's horrible for the user to specify what he wants. Even if we had a member get inside that function, then we still are splitting the definition of the customization point into two places. Because get is going to be somewhere together with the class we are specializing this for. Because it uses ADL or searches for a member. So it has to be close in the source code. On the other hand, there is some specializations of a template in the namespace std, which means we have to escape all our namespaces. So this is either going to close all of our namespaces, do this, and open them again somewhere inside the file, or we are going to have this at the very end of the file after we close our namespaces, which means our code will be in two separate places, which is not very good. All right, there's more problems with ADL. So I have a library. The library has an implementation of optional. Who doesn't, right? There's a function called makeOptional that gets a value, that uses the type, gives me an optional with that value inside. So far, so good. Inside the same library, at some place, I was doing an unqualified call to makeOptional. I shouldn't have been doing that. I should have said a namespace of the library, colon, makeOptional. But I wasn't, and it was in generic code, and the user provided me with the type that is going to be called on this thing. So it worked great, until someday I tried to compile it with GCC 7. And it didn't compile because ambiguous overloads. What? Turns out that GCC 7 actually implements the standard header optional. In that header, there's an implementation of optional and, surprise, a function called makeOptional. Somebody was passing me, it was me, but from somewhere else, I was passing a standard vector. And I was calling makeOptional on standard vector, which meant that by name lookup, I found the makeOptional in the current namespace I was in. But by ADL, I found the one in std. And suddenly the compiler didn't know which one to choose because both were equally good. So with ADL and with unqualified calls, it's very easy to accidentally start calling other code than we were before. So if you ever find yourselves writing generic code and making calls that are unqualified, better make sure that it is actually a customization point. Because somebody somewhere will start calling your functions with something that will trigger ADL. And when you've actually fixed a bug in your code to make the call qualified to disable ADL, they will file you a bug saying, you broke my code. So be very careful in generic code with unqualified calls. All right. There was a paper with the number that's highlighted there somewhere from Eric Niebler, who gives a talk on ranges tomorrow, I think. Suggested design for customization points. This paper suggested how we should start doing function call customization points instead of relying on ADL directly. So this is straight from the paper. So we have some namespace, and we have an overload of begin for arrays. And then we have some structure that has a call operator that calls begin. This looks slightly familiar, right? Should, after slides previously about swap. It's doing basically the same thing. It creates a namespace with some overloads that are the default behavior, and then uses ADL to possibly find some other overloads. But this is a class. This is meant to be an object that's called. So this is some weird like template tricks to avoid ODR violations, so to not have multiple definitions of the same thing in the binary. Again, with C++ 17 features, it would be slightly simpler. Notice the line at the bottom. This says, this is a variable. I'm defining it here. There's only ever going to be one, just like with inline functions. It just means there's many definitions, but they all mean the same thing. So now, when we call begin anywhere, I mean this begin, we name this particular begin. We will call the call operator of this structure. We will not use ADL directly. This solves a problem of some people who can't remember how to call swap or begin correctly, and who always somehow manage to make qualified calls instead of unqualified calls, and not finding the things they wanted to find, and so on. So this is the design that's been chosen as the way to do future customization points for function calls. And it's already used in the ranges TS. It's used in the networking TS. Both of those are either, one of them is published already, I think. The other is going to be very soon. And in the future executors TS, we are also going to use this exact mechanism to avoid the problems. So we will not fail to use ADL when we should have used it. And we will not have to manually do all these magic things to like pull all the overloads into our current namespace to use it in decal type to enable SFINA, or in no except to propagate the information about whether this function can throw or not. This is all nice, but so far all the techniques that we've seen, this is the status quo. This is how we do this currently. And all of them provide us a way to select something provided by the user at compile time. So either we select a different number known at compile time, or we select a different function to call at compile time, because that's when overload resolution happens. There is no coherent way in C++ to say, this is how I specialize how things happen, Whether it's at compile time or at runtime, I don't care. This is how I specialize what happens. The thing we would do to change the behavior, the runtime behavior with runtime polymorphism is we would have an interface, right? With some virtual functions. Our user would inherit from us, would re-implement the virtual functions that he doesn't like or that he has to provide because they are pure virtual or whatever. But that's a completely separate mechanism from what we've seen so far. And the user has to do it from the beginning. So it's a very intrusive mechanism. The user has to inherit, override the virtual functions, and so on. It very tightly couples the interface that we are using with the specific implementation. All right, a slight interlude or three of them. This is a rabbit, right? And it's also a duck. So some things look different depending on how you look at them, but they may be very similar. All right. Some time ago, some people decided that no C++ dog is complete without some Haskell. So here's a crash course on Haskell, which is completely wrong, but it's meant to illustrate a point. So this is 1. This is a value 1. It has a name, it has a value. This is a function. Const is a function that takes 2 arguments and returns, in quotes, the first one of them. We can partially apply functions. We can say that const 12 is a const of 12, and there's 1 argument still missing, so we can call const 12 with that second argument. All right. This is 1. 1 has a name, 1 has a value, and 1 has a type. The type is int. So this is clearly an integer, right? We can also say that const is a function. Don't bother trying to read the signature, but what it means is it takes a value of type A and of type B and returns a value of type A. This is a very weird way to say that, right? And so const 12 is going to return an int because it's going to return 12, right? Only this is a lie. Because I've specified the types explicitly, the compiler said, okay, if this is what you want, this is what you will get. But if we try to deduce the types, we will see something weird. This is a polymorphic value. So it is a value of every type that implements some interface called num. And num is a thing that is called a type class. So we can think about it as of an interface in a very rough way, in a very incorrect way. So for anything that implements this interface, 1 can be a value of that type. So 1 is really something that's implicitly convertible to everything that's a number at the very conceptual level. Same thing here, the function const12 gives us a value that's an integer, so this is a polymorphic value which follows the same rules. Okay, what is a num? This is the definition of num. If something is a number, it is going to have the 3 operators up there. It's going to have a function called negate, which will return 0 minus that thing. It's going to have ABS, which is the absolute value. It's going to have this weird function from integer, which is the way that the conversion happens. So an integer is like this type level representation of an integer literal. This is just a number That's arbitrary. So there's also some default definitions down there. So x minus y is x plus negate y. And there is also a second definition that says negate x equals 0 minus x. Those two are mutually like recursive, right? Which means that we have to provide one of them, because otherwise we're going to go infinite very quickly. What this means is there is some default definitions, but one of them has to be provided. Oh, sorry. Then we can create something like a complex number. This just means it's a struct with two members of the same type. And we can then create a value of that type, so it's a complex of two doubles. And the way we say that our type conforms to an interface, or in other ways implements a type class, is we say instance. So for every a that is a number, the complex of a's is also going to be a number. And we can define all the operations. We define the conversion from integer as just, this is the real part of this value, right? And we create negate the way we would expect to. So we negate both sides. And then we can have some operations that just magically work because of conversions. Okay, we actually implemented a bit too much. We implemented both negate and operator minus. So we can just leave the operator minus away. This is going to say there is a default implementation of operator minus. Use that one, because we have negate. Okay. Some Rust. There is some Rust talks at this conference this time, right? We have the same data type. Just a complex number that has two members, this time of concrete types. There's a trait in the standard library of Rust that says add. The right-hand side can be something different than the type we're implementing this for. But by default, it's going to be the same type. And there is a function that says add that takes two arguments, which gives us the result. We can implement the trait for our type, which is going to do the obvious thing: add the appropriate parts together, give us a complex number. A history lesson of something that almost happened in C++. C++ OX concepts. It was actually the second syntax and the second approach to concepts that was tried. The one we have currently merged into the draft of the standard is very similar to the very previous one, the very first one, sorry. But this is the second one that almost made it. So we can say that we have a concept, don't worry about the auto there. It's a concept less than comparable, which means that we can compare two values of this type and see which one of them, whether the first one is less than the second one. We can have a function that requires something that is less than comparable. This is pretty much the same as you write this with the current proposal of concept. So the numeric that we had previously would look something like this. I'm not exactly sure on the syntax because there's not really very many sources on how it was supposed to look like. But it would look something like this. And there was a feature that was probably why this has been discarded. Because nobody could implement this so that the compiler wasn't slow, way slower than currently. It was called concept maps. So say we had the same data type as in Rust and pretty much the same as in Haskel. But it's just the data. There's nothing, no operations on it. We could say that we want to map the type onto the concept. And here is how the appropriate function definitions look like. So we could say This is the definition of less. Is this plus? This is plus, right? Yeah. This is the definition of what plus means for complex. Those look similar, right? All three of them. It's a very, very similar approach. And usually when there is multiple different people trying to solve the same problem and they come up with the same solution, it means they are onto something. Sometimes it just means that nobody invented anything better, but often it just means that they are onto something. This actually works and is useful. And we've battle tested this in other languages, so we will just borrow it and just use the same thing. So here's what I tried to do. I tried to emulate this. There's going to be some macros, but don't despair. So some observations. And by the way, if I gave this talk previously and there were more macros, so there's a link at the end if you're interested in the more gory details of the macros that we are using here. All right, so a few observations. We can always specialize a member structure of the namespace we are currently in, right? And often the thing from the library that we are trying to customize is not in our current namespace. It's going to be somewhere else. But the type that we are currently defining that will be used with that something is in the current namespace. So maybe we could use that. So this is the basic idea. There's going to be some templates here. I hope you are at least a bit comfortable with them. So at the very top, there is a tag thing. Consider this like a definition. This is the type class that we are working with. I stole the name from Haskel. So the actual trait that people will use just looks into an instance within the type. The instance is defined below there on the second line with a comment. And we can just specialize that. We can specialize that template for many different tags and say whatever we want. And the actual library functionality will just look into our instances. So to not have to repeat some things. So far, I'm not actually repeating anything, but I will. There's a convenient macro. Macros are useful, as long as you don't have to look at the definitions, at which point you might run away screaming. Like, how could anybody actually write this and not go insane? Okay, one problem with this that exists, a practical problem, is that Clang format goes nuts on this. So every place I actually have code that does this, I have Clang format off, and after that I have Clang format on, which is annoying, but it works. So this kind of helps, right? But the paper I mentioned before that would allow us to just specialize anything from any namespace solves this in a clearer way that doesn't involve tricks and whatnot. But there's one problem it doesn't solve. It doesn't solve the problem of only specializing some parts of the behavior. We still have to, when we are doing the template specialization, we still have to define every member. So here's an idea. Maybe I will put the instance into the main thing. Provide like a default implementation that everybody can inherit and just inherit from it. But now there's a problem with how this is defined. The problem is that the structure that we are actually defining, the bus at the bottom, doesn't have a member that we can specialize. So we are back to square one. But worry not, templates to the rescue. This is some basically insanity that we still have to write, but if you read this from the middle and use the comments, it kind of makes sense. The void t thing works mostly like the decal type we saw before. So it checks whether the expression inside is valid. So in this case, it checks whether there is a template called instance inside the type we are asking about. If it's there, great, use that expression as the type we are looking for. Otherwise, just go to the main definition and look inside the type class. And there is a convenient alias at the bottom. So TC instance of a type class and a type just means the whole weird computation above. Nobody expects mortals to actually write code like this. And this is not something that you write frequently. And I really wish there was a way to write this more sensibly, but this is almost the best that we can currently do. Almost. So, we can do something like this. We have the same basic idea as before. We have that template that we can provide default behavior in. And we have a trait that just uses that. Unless there is a definition somewhere. Oh, these are the specializations of the main thing. Unless somebody actually uses the trick from before and specializes his own member, at which point we will use that. And he can inherit from the default implementation, no problems, right? He just inherits from the template in the type class itself. There's of course a convenient macro for this. This is very hacky, but this is what lacking a language feature to do something properly leads to. And concept maps kind of solve this because they were actually meant to solve this. All the other features, the features I'm using here, were meant to solve some completely different problems. They weren't meant to allow like using mostly the behavior somebody provided, but with this one weird difference or whatever. Okay. Some concrete case of this might be swappable. So we define a concept that means this particular type can be swapped. So there is some operation that allows us to swap two values with themselves. This macro just hides the instance thing. And we can then implement a function that the end user will use that just says, give me the description of behavior of what it means to swap two things for this particular type, and call a function that's inside. The intent here is clear. We are asking for how it means, for what it means for those two types to be swapped. And unlike with ADL, we just tell, well, swap this somehow. I don't care how you get the function, just do the right thing. Here the intent is very clear. You can see what is going on. The decal type thing and the no except thing just mean that this is a perfect wrapper, so this function is kind of invisible to the compiler in a way. It finds out whether the function that actually implements this behavior throws exceptions or not. That's the inner no except, and propagates that information upwards. And the decl type just checks whether there is actually something we can call. This is something that comes up very frequently in wrappers like this. So we want to make a function that looks nice and can be called sensibly, but we have to repeat the thing inside 3 times. So this is repeating something 3 times is a very, very common cause to write a macro, which is what usually happens here. So this is just a macro that expands to basically the same thing as we've seen previously. There is a very entertaining talk from lightning talk from C++ Now this year called "You have to type it 3 times," which basically talks about this problem. We had a proposal this last week. I was at a committee meeting, and we had a proposal that said, well, maybe if we did something like this, use this slightly different syntax, maybe this could mean what we mean when we write wrappers. And the committee said, no, let's not do that. So we are back to macro. This is fine. We can deal with macros. So by default, we will just do the old algorithm of move this thing out, move the second one into the first, move the temporary value into the second. And this is going to be the default behavior that previously we had to do using std swap, or we had to construct artificial namespaces and create function objects, which was the point of the customization point objects that Eric proposed. Now we just state the intent. Instead of we are doing some macros, but the macros are here only to steal our attention from how we do this to what we actually mean. And I strongly believe in making code look like the intent we have when we are writing this, rather than, oh, here's the workaround for that problem in the language, and here's the workaround for the other, where we have to escape all the namespaces because the language doesn't let us do anything else. Oh, and we also have to create a second type that has all the default behavior, because otherwise we couldn't inherit it. And so, just write what you mean. So for the customization point that we've seen previously, or rather all the 3 of them, I would much rather see something like this. So say it's a tuple-like. It's something that looks like a tuple. The types that you will take from this tuple are those. And oh, by the way, here's how you convert to something that looks like a tuple. Instead of doing this is the first type, this is the second type, there's n types. And here's how we get the first one, and here's how we get the second one. Just say this looks like a tuple that has these properties. Of course, this is something. Whoops, that's not exactly how it was supposed to look like. Of course, you could say just something like this with the paper I've mentioned. But then again, this solves problems. The paper solves problems. And in this case, we don't actually need a macro, yay. But if we wanted to opt into something, into some default behavior somewhere for a part of this interface, we would still need to inherit from something default. Okay, here's a little trip into trying to make macros work So far we only dealt with interfaces that were completely concrete. Here's what an interface for a counter might look like. It allows us to set the value, which is probably not something we will do very frequently, but we can get the value and we can increment the counter by 1, which is like the primary operations on a counter that we usually do when we do have a counter. Consider this an interface the same way you would consider a class that has all those 3 functions marked as virtual. This template argument just means, okay, my underlying type that I'm counting in is going to be t. So we can have like a struct counter, which is the handle to the interface, and we're going to have the set value, which is just going to forward the same for the other functions. Weirdly enough, if we want to have a default instance, we can just add the template type name t at the beginning, and it's going to do what we want it to do. Weirdly enough, I was kind of like, when I was writing this, I was surprised that I didn't have to do anything more here. Now, we have some atomic counters. So it's just a counter that uses std_atomic as the underlying value. So it's type safe. So it's thread safe, right? But there's one problem. Instead of having like an operator plus plus, which was what we used in increment here, it has a function called add, and it takes an argument. So we are going to have to do some adaptation to the interface. So default instance works with just adding the template type name thing at the top. We can try the same thing here. Unfortunately, here's where we run into problems. The error is very cryptic unless you've seen it before, and doesn't mean anything to sensible people, unlike me. This all expands to something like this plus additional code, but at the very end, the third line from the end, the template type name t template and empty angle brackets. This is not something that is valid. This is not going to work. So, how do you solve all the problems in computer science? How do you solve every problem except for one particular category of problems? Add another layer of indirection, exactly. And the one category that you cannot solve with this? Too many indirections, exactly. Let's just add a layer of indirection. This is where the templates start going crazy. The one nice property of the C preprocessor is that when you wrap something in parents, it just considers it a single thing, which is nice, but requires some additional work later on to actually unwrap this thingy. So when we define it this way, we can do something that we can also learn and remember and not try to understand how it actually works. I mean, what the macro expands to. But it's terrible. Like templates, I like templates. I'm a person who enjoys writing templates. And I was very irritated by this. That I have to go out of my way to make an interface that works, but the usage of the interface is... I don't like the usage of this interface very much. So some macros, I think this is the only slide that actually has macros, defines in them. So instance template helper, which was at the very top here, just gives us something that is in the current namespace that we can specialize. Because the problem was we were trying to specialize a template and design the template that doesn't work. So we just create a template in the current namespace. our instance inside our class is going to inherit from that template. And then we are going to have something that looks completely bonkers, but it basically says, I'm specializing the helper at the top. I'm inheriting from the default behavior. And it follows. Just define this here. This is bad, right? This doesn't look good. This is where trying to solve problems in the preprocessor gets you. You end up writing code that has some weird only macros that look like something, but look like completely out of place. Sometimes it's even fun to write macros like this, but that was only the state at the very beginning of the project until I started to have like a lot of code written this way, when it started to be like very problematic. Okay, so far I've tried to provide like a different mechanism for overload resolution, right? Nothing especially novel, and a lot of the macros just go away when you have proper language features, like I can specialize anything I want in my namespace. But there's one particular thing that's solved by both Haskel and Rust with their type classes and traits. That is, we can do type erasure with them. So not only we can resolve which function to call at compile time, we can also create polymorphic values from values that only just match the interface. They don't have to explicitly say, I am of this interface. As long as they match, you can have a polymorphic value. So it's not intrusive. We don't have to pull all our base classes into our header and inherit from them. Just say, this fits this interface, use it. And this is something that's not readily provided by C++. So this was a part of what I was trying to do here. So this is a weird way to define an interface, but it's constrained because I don't have a reflection yet. I say there is a function hash that takes no arguments, returns a size t, and is to be called on a const object. That's what the const at the end means. It's a very weird syntax to do this, but when you have a function type, you can add like qualifiers at the end. It's the same way as you add qualifiers and member functions, only in this case this does nothing. It makes the function not be a function anymore. This thing, the type that's named hash here, it's not a function type anymore. It's a weird something that can only really ever be used to declare a member function, but not define it, only declare, which is like one of the most useless things to do this way. But since this is for type erasure, so I don't know the actual type yet. So I'm just saying, okay, this is going to be a function that's callable on a const object. I don't actually have support for this implemented yet, but I know how to do this. It just, it boils down to doing a copy-paste of the same piece of code like 8 times or 12 times, something like this. Like literally going copy and paste and replace a single token every time, which is not very productive. Then I have a magic macro that says define me a type class. It takes this interface by adding definition to the name of the type class and list of member functions, which is something I have to do because I cannot enumerate the members of a type yet. I can create a default instance and I can say by default use the existing customization point. So whoever provided the definition of standard hash is still going to work with this. I tried to also do the opposite. So if I defined an instance for hashable, I tried to make standard hash work and just refer to that. There are some weird limitations of templates that don't let me do this directly. I hope I can overcome it. And then, of course, I have a nice function that just invokes the proper thing. And now the magic. That's all the code. That's all the user code, like user on the side of a library providing this. That's all the code that's necessary. And now I can say hashable : erased, which is going to give me something that looks like a value and behaves like a value, but is type erased. So I don't know the exact type of this. I know the interface. The interface says I can call function called hash on this. That's all the interface says. So that means I can call hash on it. Even though I don't know the exact type, I can just do this. And it uses the same function that we specified to be called at compile time when somebody asks for this. And erased is itself also an instance of the type class it models. So I can just use the free function. How many of you heard of the unified call syntax proposal? All right, some people. So there was a proposal to make those two syntaxes equivalent to an extent, so that both those calls would do the same. So when I've shown this slide the previous time, somebody asked me, is this the uniform call syntax? There's another thing I can do with this. I can have an object of type integer, and I can have a reference that is a runtime reference. I don't know the exact type that's underlying there. I know it's a reference. It behaves like a reference. So when I call hash on the reference, it's going to compute the hash of 456. But when I reassign the foo to 789, the next, it was supposed to say ref and not erase ref on the last line. It's just going to call the hash function on 789. So despite the fact that the way to define the interfaces is kind of clunky, and the way to define the instances is kind of bad, especially when you have templates, I like this because it enables me to write code once, say, this is what I want to happen for this particular type. I don't care whether it's at compile time or at runtime. This is the behavior I want. And I say nothing else. And I can just use the functionality whenever I want. I can type erase and still get the same exact result. And I don't have to type in all the boilerplate for creating like value wrappers for polymorphic type erasure or Sean Parent style or whatever. There is some nice things coming to C++ relatively soon. So once I have reflection, I can just say, this is the definition of the type class I'm working with. I don't want to enumerate all the members, just figure it out. And reflection, static reflection, that is static introspection into types, that is being worked on in the committee, and is at a kind of advanced stage, really, would just let me find out all the members that I have and automatically generate everything without me having to repeat anything. And the latest revision of the paper that proposes an interface for reflection at compile time also added function reflection, which means I can just make the definition look like a normal interface definition without all the shenanigans with using hash equals and that weird function type that's not a function type. It's usually called an abominable function type. And there's some particular people who fight it furiously every time they can. So with proper reflection, which is coming, with P0665, which is the paper for being able to specialize wherever. And with a proposal from Herb Sutter called Metaclasses. How many of you heard of Metaclasses? All right, not that many. It's a very interesting approach to generating code. I should be able to drop mostly all the macros. Mostly because there's still the problem of inheriting the default implementations from like somewhere else, which is not a problem I can solve without like either macros or heavy repetition. And neither of those is something I'm happy about. So this would be awesome. There is a study group on this, study group 7 about reflection and metaprogramming, which is also, by the way, trying to improve your lives whenever you have to write metaprograms by trying to make them slightly less horrible than they are currently. But my main problem with this is that for a stable interface that you can use in a production compiler without worrying about it being experimental, we'll have to wait to something like C++23, I guess, or maybe C++26, which is like 2 or 3 major revisions. 2 or 3 revisions, I should say, which is very much not optimal, but this is how languages designed by committees progress very slowly. Okay, so a big elephant in the room. Concepts. We have concepts, right? I was saying something about historical information about concepts. This is how they look like. We have concepts. They are currently in the draft of the standard, and there is a very high chance that they will land in C++20. Here's a crash course on the C++20 or TS concepts, because there was a technical specification that was meant to like allow us to iterate on this possibly many times, which did not happen. We just merged them after the first revision, as is, almost as is. Okay, so the most basic concept is the most basic concept of concepts is that concepts are constraints. So in reality, those are just values that are Boolean. We can just say that the most basic concept is true. It's true for all types. It's always true. We can say that we can have a concept that's true for all t's where we have a member that's called foo that we can call. We are just checking whether the expression there is syntactically correct. We had mechanisms for that, right? The decal type, the weird decal type thing, or the weird void t thing. This is like a more core language way to do the same thing in a way that's more understandable for the compiler, so that it can give us some slightly better errors, in theory at least. And we can say that this whole expression has to be convertible to void, which means it's basically those two concepts are pretty much equivalent. So I've been trying to somehow constrain my arrays wrappers so that whenever somebody does something wrong and gives me a value that I cannot like type arrays for whatever reason, I could have a nice error signaled by a concept. And I have failed to do it directly. So the problem is, I'm inside the definition of the type class, I'm operating on a function type. So I don't have the return type and the argument types separately. I just have one thing. There is known techniques for how to solve this problem with normal template metaprogramming. You can do like pattern matching and to like figure out what the return type is and what the argument types are, and pass it somewhere else. But there is one requirement, that is, it has to be like a continuation. So you have a function at compile time which takes the function type and takes something else, and that something else is going to be fed the return type and the argument types. I cannot do this with concepts, because concepts by design are not a thing that can be passed to anything else as an argument. So I cannot actually do something like this where explode is this magic thing that takes a function type and like turns it into its pieces. I cannot write code like this because we cannot specialize concepts. This looks like a normal template specialization, right? But we cannot specialize concepts. That's a design decision. So I cannot specialize the concept because you cannot specialize concepts. Some people suggested that maybe we should allow something like this. So generally, we want to only ever see a single definition of a concept, but maybe we should be able to like declare them and define them in a way like this. We'll see. There will be discussions about this. Maybe this is how it ends. But the only way I was able to actually work with this was by the same means as previously. So by adding another layer of indirection. Because how else? So I can turn a concept into a type by using the value, because it's a Boolean value, so I can just use it. And then I can do some magic to actually unwrap all the things that I need. This is not correct code, but it gives an idea. I have the basic concept, say fooable, so I have something that I can call foo on. So I'm checking this, and I'm referring to some values which are in turn referring to some concepts. I have no idea what the compiler can make of this. So concepts are supposed to give us like nice error messages, nice diagnostics, so that we don't have to like scroll through pages and pages of template instantiation, backtraces, and so on. But I don't know what a compiler can do with this. Like I go from a concept to add like a constant value to another concept. I don't know how this turns into an error message. I just don't know. Which is why I don't think that the concepts that we get are up to the task that I would like them to be. And also, they don't provide us a way to do type erasure. They don't have a way to like turn an interface into a runtime interface, which forces us to do all kinds of weird tricks. There is a very long research paper. This is like 100 pages or something, which tries to explore the design space of how we could make it work with like runtime polymorphic wrappers. So this is a proposed syntax, but this is a syntax that we will probably in some form have. So a shape is a name of a concept. But the way this is supposed to work is we just get a template where that shape is really a name of a template argument that fulfills that concept. So this is a shortcut. What this paper proposes is that we might actually say something like virtual. C++ is not very good at like being able to put random words in random places. So the virtual there is actually not as bad as some other choices. We are trying to get modules, and apparently by trying to get modules and making module a keyword, we broke Vulkan, and we broke CUDA, and we broke TensorFlow, and I don't know what else because the list is quite long. And all of the names on that list were like very high in the list of libraries and frameworks used in the world. So we cannot really like introduce too many new keywords. This would be nice because I could like use the same thing to define a runtime interface as for a compile time interface. But there is one problem. I cannot adapt. There is no concept maps in the current iteration of concepts. So I cannot adapt. I have to have a type that already matches the interface that somebody else expects, which is frustrating, to say the least. Okay, so in this tiny little research project of mine with the macros and so on, I still have to like implement the use of abominable function types. I want to eventually like generate concepts and try to make the compiler actually diagnose problems properly the way I want it to do it. But I'm not really sure whether that will be an improvement over the code I can write without concepts right now. I have an idea for how to allow overloading this. Although I don't know how far I should go before I actually have a usable reflection implementation where I could just do away with a lot of the tricks. And there's a library from Louis Dion, who some of you might know as an author of Boost HANA, where he implements type erasure, so the runtime part of the thing that I'm doing here. Because my current implementation is horrible, if such a phrase as virtual inheritance doesn't scare you, you haven't been through like some of the more scary parts of C++. But I have plans to use this because it's a very nice example of policy-based design, so it's very customizable without actually too much work. Okay, so some key points that I have here is that C++20 concepts need some form of customization, but every time this was tried in the committee, there was great anguish at how dare you suggest this. So I don't know how that goes. And I think they need type erasure support because otherwise we are still going to have like two different ways to go at compile time and at runtime, which leads to like very bad code, very repetitive customizations and so on. Another key point that I have here is that reflection will change how we do things. It's some of the things that will be possible with reflection are currently also kind of possible with a combination of macros and template metaprogramming, which is like the worst combination that you can have, two different levels of metaprogramming all together. So reflection, the way that it's currently being designed is going to be very nice. And there are some context for goodies. So for those of you who like writing functions that run at compile time rather at runtime, very soon we should have like support for dynamically allocating memory at compile time, which might sound weird, but allows some very interesting things to happen. Okay, here's a list of talks that are somewhat related, and I just realized I'm missing one. So the first one is Herb Satter's keynote from CPPCon from this year, Meta Thoughts on Generative C++, where he talks about metaclasses, but also about something that's called the operator space trip, which is a feature that will help us have defaulted comparison operators in a way that's sensible and customizable and so on. And will reduce the amount of code we actually have to write. Another one that should be up there somewhere is a talk from both C++ Now and CPPCon from this year. It's called Const-Explore All the Things from Jason Turner and Ben Dean, where they implemented a JSON parser at compile time. which is currently like they have to do 2 passes, but when we can actually allocate memory at compile time, they will only need 1. It's a very entertaining talk, even if you are not exactly into the kind of things like running code at compile time. Also from CPPCon this year, Louis Dion's runtime polymorphism back to the basics is where he explains how his Dino library works and what's the design behind it. And there is also a version of the same talk I'm giving here, but with more gory details about the insides of the macros that I've given at C++ Now this year. All right, and despite this saying question and answers, I have a slightly more to say, and I hope I can get at least 1 question still after this. So, the standards committee, which is often like frowned upon in the community, because what are they doing? It's a volunteer effort. And there is nobody there who is getting paid for working on C++. Well, maybe some people, but by their companies, not by the like C++ thing or by ISO or whatever. This means that if you want something changed, write a paper. And usually a champion is expected, so somebody who will present it, but you don't actually have to go to a meeting to have somebody present the paper for you. This is a very polite way of saying patch is welcome, because this is basically how we operate. Anybody who goes to a meeting can vote and can have a voice in the small groups that actually iterate on proposals and say, no, this has to be changed, that function has to have a different name, this has to work differently. But only P members, this is a term used by ISO for something that's called a participant. It's only a country can be a participant, but only a P member country can vote on actual technical documents before they are being published, and only P members can actually vote on them going into the draft. Poland is currently an O member, which means we are an observer, which means we don't have as much vote. And also because our national subcommittee that's related to the C++ standards committee isn't particularly interested in C++. It's almost impossible to actually try to get them to vote and cast a vote at ISO level. Which means that even if we became a P member, which would give us more vote, a stronger vote, ISO would quickly kick us down for not actually voting. So, to the point, if you're a company or maybe yourself as a small business or whatever, would be interested in helping us make Poland have a stronger voice on what is going on, and if you want to participate in any way, please come talk to me during the break or send me an email or something. Because to form a new subcommittee at the national level, we need 5 companies. I believe we currently have 2, which is still a way to go. But if you are interested, please come talk to me. And no direct participation is required. And it doesn't cost anything to be a member of the Polish subcommittee. But it's always welcome to write papers, come to meetings. But at the Polish level, you just only sometimes have to click some buttons in a web interface. All right, that's all I have. And I believe we have half a minute for questions, right? All right. Thank you.